Okay, so on the website, I posted a couple of PDFs with other Laplace transform values of functions. I did those using the definition of the Laplace transform. So what I want to talk about now is properties of Laplace transforms. And I'll provide a proof of these on the website in PDF form. But for now, I just want to write them down and talk about how we might use them. So the first property that I want to mention is that if the Laplace transform of f of t is capital F of s, that's just notation, then if we take that function f of t and we multiply it by e to the at, what that does to the Laplace transform is it shifts it horizontally to the right by a units. A being the same a that is in this exponential function over here. So, for example, in the last video, we found, using the definition, we found that the Laplace transform of t, which again we could write as a function of t, like a function of s, like that. We found that the Laplace transform of t was 1 over s squared. Now, using this property, if we wanted to find the Laplace transform of e to the, say, 3t times t, if we wanted to find the Laplace transform of that function, we know that we can just take our 1 over s squared and we shift it to the right by 3 units. In other words, we take s minus 3 and square it. We replace the s with an s minus 3. So that'll come in handy in the future. The next property that I want to mention is the Laplace transform of a derivative. And we are actually going to be taking Laplace transforms of derivatives of functions. And as usual, these Laplace transforms are all going to be functions of s, so we can use that notation. Now, the Laplace transform of a derivative is s times the Laplace transform of the function itself minus what's actually an initial condition, the function evaluated at 0. Another notation for that is s capital F of s minus f0. The Laplace transform of the function little f of t can always be written as capital F of s. That's a notation that we'll be using pretty commonly in our class. Now there's a proof of that on the website, but I'm not going to get into it right now. I'm going to show you the next property of the Laplace transform of a second derivative of a function. Again, it's a function of s, and it's going to be s squared times the Laplace transform of f of t minus s times the function value evaluated at 0. It's an initial condition, minus f prime of 0. Another initial condition. Now you'll remember when we're given, say, a second order differential equation, we're given 2 initial conditions. The function evaluated at 0 and the derivative of the function evaluated at 0. The case is going to be the same here when we're solving these differential equations. We're going to be given these 2 numbers. And soon enough, we will be actually solving differential equations, I promise. So that's just another property. If we want to use the other notation, which we will in our class, that would be s squared capital F of s minus s f of 0 minus f prime of 0. Now we could continue on taking a third derivative and a fourth derivative, finding the Laplace transform of those functions. I'll put them in the PDF in the notes. The third property, and it's the simplest property of Laplace transforms that I want to mention right now, is that the Laplace transform is actually linear. And what that means is this line right here. If we want to take the Laplace transform of a function that has a constant times a function plus a constant times another function, well, we can just split that thing up just like you would with, say, a derivative. You can pull the a out, that's a constant, and you can take the Laplace transform of f1. And you can pull the b out, and you can take the Laplace transform of f2. Now, that might look a little bit complicated. It's really not. Here's an example. What if we want to find the Laplace transform of this function right here? Let's see, I have it written down somewhere. Let's say 3t plus e to the 4t plus 1. Now, we know how to find the Laplace transform of t. We did that in the previous video. We know how to find the Laplace transform of e to the 4t. That was in one of the PDFs that I provided. And we found the Laplace transform of 1 as well in a previous video. What we can actually do, if we want to find the Laplace transform of f of t, is we can split this up into 3 pieces. And you can do that in your head, but I'm going to write it down as an extra step. Even further, this 3 in the Laplace transform of 3t, since it's a constant, we can actually just pull that right out of the Laplace transform. Again, it's something that you'll just do in your head eventually. I'm going to write it down this first time. So if we want to take the Laplace transform of that function, which is 3 terms, we just take the Laplace transform of each part. Laplace transform of t, we found it in the previous video. It's 1 over s squared. So I'll write it like this. Of course, that just becomes 3 over s squared. Laplace transform of e to the 4t, which is on your list, or it's on the PDF that I provided for you, is going to be 1 over s minus 4. The Laplace transform of 1, we found it previously as well, which is 1 over s. So your final answer, the way that you would write it, say on a test or in the middle of a problem that you were doing using Laplace transforms, would be that right there. We just used the third property that I provided with you. It's a linearity property. To split that function into 3 different pieces and take the Laplace transform of each piece.